Get started. So welcome back everybody to EE240. So just a couple of administrative things. So first of all, obviously the project is due tomorrow. So hopefully most of you guys are well on your way in terms of that. This is phase 2, of course. And for those of you guys who are paying very close attention, I actually posted phase 3 of the project up on the web late last night already as well. So if you did actually finish, then I definitely strongly encourage you to go ahead and take a look at that. So as I've sort of written on the slide here, right now as it stands, phase 3 of the project is due basically 2 weeks from tomorrow. So that's Friday, May 7th. Now, last year I actually pushed back that deadline a little bit because I wanted to make sure everybody had enough time to really kind of go through the whole thing and really make sure they sort of got the full benefit, so to speak, of doing the project. But for this year, unfortunately, the final is scheduled a little bit earlier. So the final is scheduled for Wednesday, May 12th. So the question that I have to you guys, since you're here in person, I guess you get the special bonus. I'm okay with pushing back the sort of due date of the final phase of the project by, let's say, a couple of days or maybe even up till Monday. But obviously the trade-off there is that that'll give you sort of less time to study for the final. So let me maybe just sort of take a little bit of a census poll. So if I was to offer you to push back the due date of the project to, let's say, I don't know, Sunday, May 9th, which, by the way, also means that we'd probably have to come in over the weekend and do, you guys would do your presentations over the weekend. But if I was to push it back to that, who thinks that they would want that to happen? Raise your hand. Okay, so, you want even an extra day? I mean, I'm fine with pushing even one more day, but it's just, again, a question of, actually studying for the final. So even one more day? Okay, well, all right. So I'm okay with that. The only point is that that's obviously going to give you like a day to study, which means that there'll be like 1 day to hold the review session. And as you remember, when I hold the review session, I don't have any material prepared. It's just you guys should have questions. So if you guys are comfortable with coming in the next day and asking me questions on the final, that's totally fine with me. Maybe just in case you're counting the hours, I believe this is at 11:30 a.m. on Wednesday. So you're not even going to get that extra like 12 hours or whatever it is for late exam. So maybe just to double check. So I'll put this out as the sort of final proposal. So project due, let's say May 10th in the morning. That's Monday, May 10th in the morning. Raise your hand if you want that.
We'll be studying as part of the project.
Okay. All right. Sounds good. So I'll shift the project due date to that. If anyone has any very strong objections, come and bug me. But yeah, I think we'll do that.
Final on that day.
Okay, so it will probably be that day. If you can't make it, hopefully your partner can. If not, bug me and let me know. We'll figure something out. But basically, pushing back the due date means that that's when the presentations will be as well.
Would we be able to just like present a day earlier or something?
Say that again?
Could we present like a day earlier or something?
Possibly. I'd like to sort of keep all the presentations together because obviously part of the point of doing this is you get some feedback from your classmates, you get some feedback from me. Right, everybody. It's always good for everybody to see sort of what was done and how things were done. So that's possible, but I'd prefer to keep everyone on the same day just because I think it's the best learning experience for everyone. Okay, any kind of questions on either the project or materials or stuff that we've been talking about so far? Yeah.
So one of the categories on the simulation results was VDIF plot showing worst case voltage rise. Could you draw what that is, maybe, or explain it?
Okay, so all that means is, remember, we're sending sort of random bits as we're trying to communicate things back and forth, right? Mm-hmm. So the point here is that because your amplifier has limited bandwidth, basically not all, like for example, if I was sending, well, I guess to maybe state the obvious, if I send a long stream of zeros, right, then clearly the amplifier is going to completely settle out, right? It's going to give you exactly A times that DC thing. Right? So what that really means is just that, okay, if as an example I had sent a really long string of zeros, and then a single one, and then again a really long string of zeros, right? Then we know that just because this is a very simple case where we have like a first order amplifier, right? Then we know we'd have to go all the way from what was being transmitted as a bunch of zeros up to approach what we should eventually get if we had a long string of ones, right? So as an example, you might have seen something that looked like that, right? So that's basically what was being referred to in this particular case here. Okay, that was essentially just given that we had a very simple quote-unquote channel, our channel is really just the amplifier, which is really just a first order low pass filter, you can pretty quickly figure out that that's kind of the worst case thing you can do.
So you feed in a single pulse.
That's right.
Okay.
That's right. Now, that's not true for all channels, by the way. So particularly things that have like reflections in them that look like that, if that's like the frequency domain response, if I have a really deep notch somewhere, I might actually have a different worst case sequence. As an example, you can imagine if I was transmitting like a bit pattern that happened to sit exactly in that notch, really bad.
Okay.
Right? Does that make sense?
Yeah, no, totally.
Okay, great. Any other questions on either project or material? Yeah.
Combine equalizer and preamp together?
Not necessarily. So obviously it depends on sort of how much gain you need in the receiver in the first place. And in fact, one of the things that I'll encourage you to do in the third phase of the project is really think about, and in fact maybe even in the second phase, is think about, okay, what's kind of like the best way to partition things? Meaning, should I just put more swing in the transmitter versus add maybe an extra stage in the receiver to get that extra gain, right? So the real question is, depends on what's really the right thing to do from a power standpoint. Right? And so obviously that's going to depend on how fast you're going and basically how much capacitive load you have at the receiver versus what's the impedance that you use to transmit on the transmitter, right? So no, not necessarily. It could indeed be two separate things. Just as sort of a little bit of a side note, if I really have a pretty bad channel, right, even if I'm doing sort of a two-stage type of design, there's kind of an interesting trade-off that you might get into. Okay, so let's say that this is on my transmitter. Let's say I have this as a preamp and that as my equalizer. Okay, so there's a little bit of an interesting trade-off here. So if I have a really bad channel, that kind of means that the things going in at this point could have really big sort of variations on them. All right, like for example, if I transmit a long string of zeros, I could get a really big signal. But if I only do like this little lone one, I might get only like a tiny little pulse out of it, right? So what that means is that in some sense, the dynamic range that this preamp needs to handle can potentially be pretty large, right? Because basically if I have this low pass filter and I want to recover things that are all the way down over there, then that kind of means I need to be able to handle this dynamic range, okay? So if I just put this directly into the preamp, and I have pretty big transmit swings, which by the way, for a long time, that's what people have been doing. So, typical swings that at least, let's say 5 years ago, were about like a volt peak-to-peak differential. I'm not joking, right? That then means that this preamp here would have to handle that full 1 volt huge signal and all the variations on it, right? From a linearity standpoint, that can get pretty tough to actually do and really recover things correctly, right? So the difference with the equalizer is, depending upon how you've built that equalizer, that thing may actually reduce some of the dynamic range, right? Because when I build the equalizer, I'm kind of intentionally flattening this whole thing out, right? So you may, in fact, actually want to reverse the order there. You may even want to put the equalizer first and then the preamp. On the other hand, from a noise standpoint, you may actually be paying more noise by putting the equalizer first, right? So that's kind of a side trade-off. You probably won't deal with that too much here because if you do things right, you probably won't have that huge of a transmit swing. But something to be aware of because in practice, that's certainly something that happens. Yeah?
For this phase of the project, so...
This phase means phase 2 or phase 3?
Phase 2, yeah.
Okay.
So can we, the circuit diagram as you've given it, the common mode of the transmitter and the receiver are the same, right?
Yes, so you have to DC couple.
So, what frequency can we assume? What I'm asking is if it works for the bit stream which you're given, is it fine?
You mean in phase 2?
Yes.
Well, so again, just be careful that you actually check, what you think will be the worst case pattern. The channel that I gave you is not too bad. But yes, if it works there, then it's reasonably good assumption that it should actually work. Now, if you've done something funky in your equalizer, that may not necessarily be the worst case thing, right? So you have to look a little bit more carefully at your equalizer and see, okay, is there something actually I could do that would be worse? But most likely, what I gave you is fine.
So does the capacitance, is there a limit on the maximum value because you're going to anyway...
The input cap of the receiver, you mean?
No, the DC coupling caps.
No, so that's what I'm saying. You can't put AC coupling caps.
Oh, okay.
You have to be DC coupled.
Oh, okay.
Because I never said the data is DC balanced.
Yeah. Okay.
Right? So by the way, just in case it wasn't clear, For phase 3, I explicitly said in there, no AC coupling caps. In fact, for phase 3, just in case you were wondering, I used to let people use different supply voltages on the transmitter and the receiver. Same supply voltage everywhere. So if you want to muck around with the common mode, you'll have to figure out how you do that. It's not too hard, by the way. So in some sense, that makes things a little bit harder, but it also makes things easier because you have less degrees of freedom, so you sort of have to do one thing or another. Yeah?
Okay, so if you're changing the common mode, can you use a voltage source? Or
Nope.
no? Okay.
I mean, I'll put it this way. If you were building a chip, where are you going to get the voltage source from? So if you know how to build voltage sources on chips, then let's talk, because I want shares in the startup. Any other questions or? Okay, so let's actually go ahead and sort of dive back into where we were last time. And as you'll see in sort of phase 3 of the project, some of the stuff we're talking about today is going to turn out to be fairly important. So last time we were essentially talking about device mismatch, and really, as we'll see, we're going to use that to kind of get into how can we predict offsets that we might get in things like our amplifiers, our comparators, and so on and so forth. So where we basically ended up last time was talking about kind of the different categories of device mismatch. And what we said was that really what we're mostly going to care about is so-called local device mismatch, meaning with two devices that are like right next to each other, how closely matched will they actually turn out to be? Okay? Because all of these other sort of categories, if we've done a good job, shouldn't really directly impact the performance of our analog circuits. Okay? Even though actually some of these variations can be quite large. So it's not that you can sort of completely forget about these, but most of these variations have to do with sort of like maybe shifting the overall bias point. But they won't usually cause mismatch between the devices. Okay? So if we take a look at sort of the local variations, which again we said are the ones that are really sort of going to be the most important to us, there's again sort of two different categories we can come up with here, or two different types. The first is so-called deterministic sources. Okay? And what I mean by this is you basically, something in your layout causes these two devices to intrinsically not be exactly the same. Okay? Something is sort of causing some mismatch there. And when I say it's deterministic, that means like if you knew everything about the process, you could actually predict exactly what the error you created was. Now, unfortunately, the process is pretty complicated. There's lots and lots of weird effects that could come up. So sometimes it's actually hard to really predict what these deterministic sources will cause. But basically, they're certainly there, and they're something you need to be careful about. Okay? The other one, which we're gonna spend most of our time focusing on today, is sort of the random sources of variation. Okay? So let's maybe just sort of see where each one of these would come from, just really briefly. So in terms of the deterministic sources, that's usually things like, again, just something in your layout is not quite exactly right. Okay? So let me just sort of draw an example. So just an example, if I take one transistor and I draw it like that, versus I have another transistor like this that happens to have another transistor next to it. Okay? Well, turns out this transistor will definitely not behave the same as that transistor, nor will it behave the same as that transistor. Okay? And there's a whole bunch of reasons why. So one simple example, which I'd mentioned I think way back in the beginning of class, is turns out the speed at which you actually etch the poly depends upon how much other poly there is around. Okay? Or how much final sort of poly you want to stick around. So in other words, this device right here might end up having a shorter channel length, ever so slightly, than this device right here. Now, in fact, that's actually a sort of fairly classical effect. When you get into sort of 90 nanometer and below technologies, you get all kinds of other fun. Okay? So as an example, in 90 nanometer, people are basically doing things where they essentially are stressing the transistor. Either they're like pulling the channel apart or compressing it in. Okay, that turns out to improve the drive currents. Well, when they add these stress layers, basically that's like a mechanical structure, right? And so actually it depends upon what else happens to be around it. So as an example, if you have like two transistors like this, you'd see that depending upon how far away you put this other transistor, because that impacts the stress liner, you could actually change the amount of current that's flowing through this device right here. Okay? So bottom line, there's lots and lots of ways that things can sort of interact with each other. But the good news is that if you do a good job, and we'll see later, just maybe briefly review what are some of the good things to do to actually do a good job. If you do a good job, we're going to assume that most of these you can basically eliminate. And again, that's really just about sort of good layout practices. So what we're really going to be left with, which we're mostly going to focus on, is these so-called random sources of variation. Okay? These random sources, again, actually come from some pretty interesting places. So the one that actually most people spend a lot of time worrying about these days, and actually worried about for quite a while, is so-called dopant fluctuations. So what this means is literally how many dopant ions were implanted inside of the channel of my device, of one particular device, versus the device right next to it. Okay? And the reason people are really worrying a whole lot about this these days is if you looked at like a modern transistor, particularly things that you use like in your digital logic, so a pretty small device, let's say something like, I don't know, 200 nanometers by 90 nanometers, or even half a micron by 90 nanometers, turns out you could almost count the number of dopant atoms that are actually going to be in that thing. So like for a 90 nanometer device, you're probably looking at order 100 dopant atoms. Okay? That means that if it just so happened that one extra dopant atom made it in there, or one less dopant atom made it in there, actually that's pretty substantial, right? That's like a 1% change in the total doping, right? And you can imagine the way they do these things is they literally are just shooting ions inside of there. They're not like sitting there counting, oh, that was 1, that was 2, that was 3, right? You just sort of bombard the thing, and however many you get, okay? So in fact, if you really were to scale this to like, probably even let's say like 22 nanometers or so, you can even get down to about like 20 to 30 dopant atoms per like minimum size device. Okay, so clearly big source of random variation. Okay. The other one, which is perhaps a little bit less obvious, but when you think about it, maybe should be clear, is when I drew these transistors here like this, if I zoom in on kind of like that piece of poly right there, it doesn't look like nice perfect straight lines. It actually sort of looks like that. Okay. There's some roughness all along the edges there. Okay, that's just because obviously you can't print anything perfectly, right? If there happened to be a photon right in this spot versus not, that's going to change exactly how you etched that little piece out. Okay? So you can imagine if I actually have this inside of my channel, we like to think of having just a certain L and a certain W, but obviously, this thing has some weird composite of L and W, right? So depending upon what exactly that weird composite was, you might get slightly different electrical characteristics. Okay? There's also things like oxide traps, again, a whole bunch of other sort of more detailed things, but bottom line, there's lots of things that are really basically truly random variations. And again, when I say random, that means that you can't predict ahead of time what the actual value will be. You can only say something about the statistics of those variations. Okay? So let's kind of, we're going to mostly take a closer look at these random components, because again, everything else we're going to assume we can handle by sort of using good layout practices. Now, of course, a lot of these phenomena that I was talking about are really just the fact that no two transistors match each other is by no means a new problem. Right? This has been around for a long, long time. So there was actually quite a bit of basically in-depth studies that a whole bunch of people have done to really try and understand these issues and really the mechanisms for variation. So the classic reference for sort of MOSFET mismatch is this paper by Marcel Pelgrim. Okay, so this was done back in 1989. What they basically did is took a whole bunch of wafers that were being fabricated at Philips at the time and basically built some fairly careful test structures to really very, very sort of precisely characterize exactly what was the mismatch they were seeing between pairs of nominally identical transistors. Okay? Turns out to really measure this correctly is kind of tricky because you can never quite tell if the mismatch you're measuring is because it's really mismatched or because you basically made a mistake in sort of how you laid it out and you had some small deterministic error left over there. Okay, but basically this sort of Pelgrim paper, they're sort of the first ones that really came up with a model for how should mismatch behave. And still today, this is like the classic reference. So if you've never read the paper before, definitely encourage you to go back and kind of take a look at it. It's pretty old, and in a very old technology, but actually the model is still basically the same model that we use today. Now, obviously, a bunch of people have followed up on this, so there's many more papers afterwards. This one's sort of a particularly reasonable one to look at. This is by Kroon and Willie Sanson and a few other people. They basically sort of updated this a little bit with some more modern data, but really the sort of the quote-unquote default thing you always should go back and look at is really that Pelgrim paper. Okay? So let's see sort of what the key ideas there really are. So again, as I'd mentioned, in terms of these random sources of variation, in terms of how they cause mismatch, that's really what we're basically saying now is that they're really sort of set by the composite of many small individual and independent events. In other words, did this particular dopant atom make it into my channel or not, right? Or did this photon happen to hit my piece of the gate or not? So the key assumption that we're basically making here is that the correlation distance, meaning whether or not, how, like, spatially, whether or not this event has anything to do with something right next to it, is a very, very small thing. Okay, so you can imagine if it's something like a dopant atom, that's one atom, right? And whether or not that one atom exists there, kind of it doesn't care whether there's another atom next to it or not. Okay? So what we're kind of saying here is that if each one of these things is essentially independent of the things next to it, and that each one of them is a relatively small effect, then we're going to kind of assume that essentially linear superposition holds, meaning that we're just adding up a bunch of small little effects to figure out what the mismatch between two nominally identical devices should be. So for those of you guys who like statistics and stuff like that, that basically means that if we're adding up a bunch of small linearly independent events, then no matter what the distribution of each one of those events is, the total distribution I measure at the end should be a Gaussian distribution. And again, for those of you guys who like statistics, this is just central limit theorem. Okay, just a bunch of small independent events. You add them all up, you should get a Gaussian at the end of the day. Okay? So just like with sort of noise, we're going to model mismatch as being a zero mean with some Gaussian distribution. So the name of the game is going to be, how do we figure out what the variance of that Gaussian distribution is, and how does it depend on our design parameters? Okay? Okay, so turns out the sort of the basic model for what we're going to do to figure that out is actually very, very simple. So for just about all of the parameters that we're going to care about as an IC designer, basically for any one of those parameters, if I wanted to know what was the variance of the mismatch in that parameter, so let's call P, this is just like the parameter that I care about, that mismatch is going to be some AP squared. This is just some constant that's going to be basically given to you by the technology guys, divided by W times L. In other words, the active area of the device, plus some other proportionality constant, times the distance between the two devices that we're interested in squared. Okay? So where does this come from? Well, what's basically going on here is we're saying something like the following. Let's say that this was like the gate area of my device. Okay, so that's like the piece of poly. And let's say that we're talking about something like, how many dopant atoms are inside of there, right? So if I have a certain like dopant atom density that I'm trying to hit, what that basically means is, okay, inside of that area, there's going to be some number of those atoms that are going to show up inside of there or not, right? Well, since this is random, if I make that area bigger, then basically what I'm saying is that, okay, again, I'm going to have a bunch of random sort of hits inside of that box. But because the box is twice as big, I'm basically averaging out more of the variations in how many really ended up inside of there, right? Because I have more chances to just sort of smooth out if I happen to get some really weird event, right? So that's really kind of the basic thing of this model. It's just saying, whatever the parameter is, there's some proportionality constant that's related to the technology. And then if I want to predict what's the variance, it's going to be reduced by the area of the device. Okay? So just be careful sort of in terms of the units here. This proportionality constant, again, it's multiplied by area of the device. Okay? In other words, if you want to reduce the sigma of the mismatch by a factor of 2, you have to quadruple the area, okay? Because it's, again, sort of just you're summing up a bunch of random events, okay? And when you sum each of those random events, obviously the variance just goes as the root sum squares, okay? Does this kind of make sense to people, or? Okay, now, so what I'm going to do next is just sort of walk through a few of the individual pieces of what can actually be mismatched and basically where the technology constants are going to come from. But pay attention, just even from the form of this already, it should be pretty clear that this could actually be a pretty big problem. Because the trick here is that, again, since this thing depends upon the area of the device, half of the point of scaling, or actually I should say all of the point of scaling, is to make the devices smaller, right? That means you have less opportunity to actually average these things out. And unfortunately, if you actually want to fix mismatch, well, we'll talk about some more clever approaches, but a lot of the approaches basically just boil down to you have to make the device bigger, okay? Oftentimes when you have to make the device bigger, that basically means you have to spend more power than you otherwise would have wanted to. Okay? And you can actually do some very sort of basic calculations. In modern technologies, if you don't do anything else, mismatch can actually turn out to be the dominant cause of forcing you to dissipate a certain amount of power. Okay? So that's why we're actually going to spend some time talking about all of this. Now, just before I move on, one other thing I should mention, I included this like distance proportionality constant, this SP over here. Again, that's just saying that if I have two devices that are supposed to be nominally matched and put them right next to each other, versus an example, I put them, I don't know, 100 microns apart, clearly the farther apart you put them, the worse the mismatch is going to be. Okay, that's what this sort of distance proportionality constant is doing for us. But as we'll see, and as probably is sort of obvious, if you do a quote-unquote good job with the layout, this term, generally speaking, you're going to try and make go to 0. Okay, you're going to try and make it so that, in essence, the devices are literally right next to each other, even if the devices are really, really big and you can't exactly make them truly right next to each other. Okay? Does this kind of make sense to people, or? Okay. So the first and probably the most dominant sort of form of mismatch that you're going to be worrying about turns out to be the threshold voltage mismatch. Okay? So if we look at sort of what's the form of that threshold voltage mismatch, it's exactly the same as what we just said a second ago. Basically, the sigma squared is just set by some AVT squared, again, this comes from the technology, divided by the area of the device, plus this distance-dependent term. Okay? So this plot here is just basically showing you that, indeed, if you go and you take the measurements, this is, by the way, from the Pelgrim paper, if you go and you take the measurements, indeed, basically, it follows this trend very, very well. Okay? So for like the 2.5 micron CMOS process that they were working with, the AVT for the NMOS device was about 30 millivolts times micron, and the AVT for the PMOS was about 35 millivolts times micron. And again, notice the units here are indeed correct. It's millivolts times micron, because when you square this up on the top, you'll get millivolts squared times micron squared. And when you divide it by the device area, that knocks off the micron squared. Okay? So just a sort of like, you know, a quick maybe thought process here. So if my AVT was 30 millivolt micron, and I had, let's say, a 1 micron by 1 micron device, what does that say the sort of the sigma squared of my threshold mismatch is? Or let's just even do the sigma of my threshold mismatch. And let's assume that the devices are right next to each other.
30 millivolts?
Yeah, 30 millivolts. So how many sigma do you think you usually need to worry about? Roughly.
3 sigma.
Okay, 3 sigma. How did you come up with 3 sigma?
95%.
Okay, yeah. Basically, if you want, let's say, 95% or 90x%, I don't remember. I think 3 sigma is actually more than that. But if you want 90x% of your devices to work, then you should cover like 3 sigma variation, right? Okay, so that means that for a 1 micron by 1 micron device, I would have had 90 millivolts of sort of expected mismatch that I should deal with, right? How big was the signal swings most of you guys were using in your transmitter? Just ballpark.
60 mil, 15 mil.
60 millivolts. How much?
100,
15.
100.
100. Oh, okay. Well, okay. But actually, even with 100, if I had 90 millivolts of threshold mismatch, I'm in bad shape, right? I've only got 10 millivolts of signal actually left, right? So clearly, this is a pretty big deal. Now, the good news is, as we'll talk about in a second, this number, this AVT number, gets better with technology. The bad news is, I don't think you had any devices that were even close to 1 micron by 1 micron in area, right? So actually, some of this, like about 90, 100 millivolts of threshold mismatch, pretty common. Okay, definitely not unheard of. I mean, those devices are reasonably small, but actually, I would not be surprised if those are the kinds of range of threshold mismatch you'd be dealing with. So that kind of the point here is user beware. This is a pretty big deal. This is usually the kind of the number one thing you have to deal with in terms of mismatch. Okay? Now, when I gave you that equation there, the sort of natural question to ask is, okay, is that really sort of always true? Or is there some other sort of weird impacts that I can get, for example, by biasing the devices at different spots? Okay? Well, so turns out, if we sort of play around with, for example, the VDS, largely speaking, the threshold mismatch doesn't change a whole lot. Okay, this data is a little bit old, but it just kind of shows you that moving the VDS doesn't seem to change the sigma of the threshold mismatch all that much at all. And just to be sort of totally clear, the experiment that was being done here was they're literally just taking two devices, with the same VGS, and then essentially for each, and then, oh, actually I should do this. And then for both of them, they were moving the VDS around, but they were measuring what was the change in threshold between these two as a function of that VDS right there. Okay? So largely speaking, it's independent, but we'll see in 1 second, particularly in sort of modern technologies, this kind of changes a little bit. So it changes ever so slightly. By the way, maybe just to sort of prefetch a little bit, anybody have an idea of why I might expect it to actually change as I change the VDS? You said something, just speak up. Dibble. Okay, so how would dibble affect things? Okay, so dibble would say that the VT for both of these devices would actually decrease as I increase the VDS. But the question now is, should that actually change the mismatch between them? So by the way, the plot says no, but I'm going to claim that maybe there is some small effect there. So I'll leave that as a small puzzle for now. We'll actually come back to that, because as we'll see in 1 second, there is something that definitely does change. Okay? So even in these older devices, if you actually change the substrate bias, meaning the back gate or the source to the body, that actually does seem to have a very strong impact on the threshold mismatch that you measure. Okay? It turns out the thing that I was hinting at a second ago with why the drain may actually matter a little bit too, physically it's kind of the same reason as to why this back gate actually has an effect. Okay? So to see why that's the case, let's maybe just sort of draw a little cartoon picture of our transistor. Okay, that's N+, that's N+, and I've got the channel region in the center, of course. Okay? So remember we had said that a lot of the stuff that people were worrying about had to do with just random dopant fluctuation, meaning how many dopant atoms happen to be sitting inside of the channel versus not. Because remember, the number of dopant atoms you have directly impacts your threshold voltage, right? Because however many dopants you have, that's how many fixed sort of ions you have to image on the other side to actually get the channel to invert. Okay? So let's just draw some sort of pseudo-random profile of dopant atoms that might be happening to sit inside of the channel. Okay? So when the thing is actually operating in saturation, I get some depletion region that, let's say, looks like this, right? So what happens if I go and I apply some bias on the substrate relative to the source? What happens sort of inside of the transistor? particularly from the standpoint of the threshold voltage?
Increase.
Say that again?
Increase. Increase.
Okay, the threshold increases. Why does it increase?
More depletion region.
Ah, the depletion region gets bigger. Okay, so if the depletion region gets bigger, let's just say as an example, it happened to do this, right? Okay, so that certainly increases the threshold voltage. But if I had another device that even though the layout was exactly the same, it had a slightly different pattern of random doping. Remember, the reason the threshold goes up is because I included more of these dopant ions, right? Well, what if in that other device, rather than picking up 4 extra dopant ions, let's say that, in that other device, I'll just draw it in blue. Let's say that another device, somehow magically, every single dopant ion except for 1 happened to land in the same spot. Okay, but this particular dopant ion in the other device happens to be sitting right there. Okay? Well, in that case, rather than picking up an extra 4 dopant ions, I'd only be picking up an extra 3, right? So in other words, the exact threshold I get would be different between the two devices, right? So that says that because this sort of substrate bias is changing the depletion and is changing exactly which dopant ions you pick up versus not, you'd actually see that the threshold mismatch changes as you change that substrate bias. Okay? So now, just to make sure that this is sort of clear, why was it that I was kind of hinting at maybe the drain voltage actually could matter a little bit too? Why was I hinting at that?
Drain-induced barrier lower.
Right, okay, so what does drain-induced barrier lowering mean? What's sort of changing?
So the depletion region between channel and the drain.
There we go, right? So when I put some voltage onto the drain, that impacts the depletion region on this side, right? So again, because it impacts that depletion region, I could be picking up a slightly different number of dopant atoms, okay? So again, that's a relatively small effect just because hopefully the dibble is small to begin with, because if it's not, then you don't really like the device you got anyways. But keep that in mind, because indeed there's a small variation that you can pick up there, okay? So this is actually, again, sort of a good news, bad news case, because in modern technologies, the dibble is probably a lot worse, but the substrate effect is probably a lot smaller, okay? Because with the modern technologies, the doping is so large that the body effect tends to be pretty small. Was there a question in the back? Or? Okay, I answered it already. Okay, good. So, any other questions? Or? Okay, so let's sort of take a look at, we looked at the threshold voltage, so we can also take a look at, well, okay, how does the bias current mismatch, or actually just how does the drain current mismatch between two devices, how would that move around, for example, as we, let's say, change the VGS on those devices, okay? Now, hopefully it should be fairly obvious that as you move the VGS, the amount of change you measure in the bias current should really directly depend upon that VGS. So why should that be sort of obvious? Why is it that changing the VGS should really drastically impact the amount of current mismatch you measure? Any thoughts? Roughly speaking, what sets the ID? What is it related to?
Mobility.
Okay, yeah, there's mobility in there. What else? I mean, specifically in terms of this. Not a trick question.
VGS.
VGS, okay. Just VGS by itself, or
VT.
minus VT? Okay, so what did we just spend a lot of time talking about? What type of mismatch? Yeah, we just talked about VT mismatch, right? So if I take a particular device, really a pair of devices, and I say that this device on the left, let's say, has 20 millivolts or 50 millivolts of extra VT on it, right? So let's say it's got an extra, so I'm comparing the device with something like that versus the device with just VGS minus VT, okay? So what's going to happen when I make VGS really small on both of those devices? why is that going to make the current mismatch a lot bigger?
VT matters more.
Yeah, basically, as a relative percentage, this fixed delta VT matters more, right? Because if I used to have a VGS minus VT of, let's say, 100 millivolts with a delta VT of 10 millivolts, and I drop it to like 50 millivolts of VGS minus VT, now I went from like a 10% effect to like a 20% effect, right? So by the way, just to use sort of the same terminology we've been using all along, when I say VGS, you can sort of take that as a proxy for V star, right? So clearly, if I reduce the V star, then some amount of fixed delta VTH is going to cause a larger amount of current mismatch. Okay, so that's kind of why you see this trend that looks like this. As you decrease the VGS, you see the current mismatch going up. So now, let's say I took this out to like a ridiculous point and I said, okay, I really don't want any VT mismatch to impact me at all. So you had like 10 volts of VGS on this device. Would you go down to 0 mismatch in the current, or is something else going to kick in?
It's going to break down.
Say that again?
It's going to break down.
Yeah, okay, yes, the device will break down, but even ignoring that minor quote-unquote detail, is something else going to happen? Can I get 0 mismatch out of the devices by sort of, giving them infinite VGS? What does current depend on? You mentioned one of them. You already mentioned mu. What else does current depend on?
Yeah.
Okay, it depends on COX. What else does it depend on?
WL.
W and L. Okay. We talked about VT mismatch. Is there any reason to believe that any of these don't vary?
The aux will change.
Yeah, all of them vary, right? All of them won't be exactly the same, right? Because mobility, again, I had a slightly different number of dopant atoms in one device versus another. COX, I happen to have, I don't know, I mean, these things are thin enough that even having one electron there versus not would kind of matter. I'm not sure exactly how I'd measure that, but COX is certainly going to vary. The W and the L, as we just talked about, you can never print them exactly the same, right? So all of those are actually going to vary, okay? So in case you're sort of paying attention to the very next slide, usually this is called variations in sort of the current factor, or beta, right? Where for a long channel device, beta would have just been mu COX W over L. Okay, even for short channel devices, just take beta as being the relationship between VGS minus VT and like the proportionality constant that you multiply it by to get back to current. Okay? So just like with threshold voltage, actually there's going to be mismatch in the beta. Okay? The beta is never going to be exactly the same between two devices, and that's really all this plot here is showing you. Now, because physically, again, this is coming from things that generally depend upon the area, just like with threshold mismatch, you can see it depends on the sigma basically goes with 1 over the square root of the area. Okay? So let's actually sort of take a closer look at, again, what those sources are. So as we'd already mentioned, the mobility mu isn't really going to be exactly the same between two devices. Again, either because there's some random number of dopants inside of the two, and remember the number of dopants you have changes the mobility, or because one of them happens to have a random defect in one spot on the crystal versus another one that does not, right? But basically, all of that stuff is just related to the mobility. As we also mentioned, the oxide thickness may vary ever so slightly between the two. The good news is this one is usually really, really well controlled because they're already so incredibly thin that just, if there was one less atom there, that's like 50% of the thing is gone. Okay, so usually that doesn't happen. So, there is some variation here, but it's very, very, very small. The last one, which is kind of more interesting and sometimes starting to matter a little bit more these days, is again this edge roughness that we had talked about. So basically, as we had said, even though I may draw my transistor looking like this, when I actually print it, it may come out looking something like this. Okay? So let's actually sort of put all of these together to try and come up with what should be like the model for our total beta mismatch, our total current factor mismatch. So what I'm going to look at here is, because this is usually the way this thing is specified, is I'm going to look at the variance in that current factor normalized by the nominal current factor. In other words, this is kind of like saying there's a 1% relative variation or a 10% relative variation or so on and so forth. Okay, because usually the absolute number here is not quite as useful. It's really the relative variation you care about. So if I want to know the relative variation in that current factor, if I assume that each one of those like physical parameters varies independently, then I can kind of say that the overall mismatch should just be related to kind of like the sum of the variances of each one of those parameters, right? Relative to its nominal value. So as an example, if I have some mismatch in the width, I would say, okay, there's some variance of the width divided by the nominal width squared, plus some variance in the length divided by the length squared, and so on and so forth. Now, there's actually kind of a pretty interesting effect that you get into here. So it turns out that if you think about the variance of the width and the length, they actually depend on what was the other dimension that you used. In other words, if you want to know the variance of the effective width, you actually need to know how long the transistor was. Okay? So maybe just to sort of see if anybody can see why this is already. Any ideas? Why is it that if I want to know what's the variance in the width, I should actually figure out what the length was? Or similarly, if I want to know the variance in the length, I should know what the width was.
Do you have more samples if you have, like, you have more width samples if you have a longer length?
Yeah, exactly. Right? So let's actually draw this for people who don't see it. So let's say I have some transistor with these fuzzy edges here, right? So let's say that's the length dimension. This is the width dimension. Okay? So now, let's say that I'm interested in the effective mismatch on the width. Okay? So if I'm interested in the effective, actually let me do the length because it's a little bit easier to draw. So let's say I'm interested in the effective mismatch of the length. So if this was my transistor, kind of the only reasonable way to come up with what the length of that transistor is to cut this thing up into little sections and say, okay, on this section right here, the effective length was this thing. On this little section right there, it was a little bit wider. On that little section right there, it was again a little bit wider, and so on and so forth, right? So just like Sean just said, if I was to make this thing wider, what I'm basically doing is I'm adding on more sections for me to average out, right? Because the more sections I have, the closer I should get to actually averaging out to exactly the number I wanted, right? Does this kind of make sense to people, or? Okay, it turns out it's the exact same thing, obviously, in the other direction too, right? So in the other direction, rather than having sections that go like this, in the width direction, it would be sections like this, meaning the longer you made the device, the more you'd average out the changes in the effective width. Okay? So what this basically says is, if I want to, again, sort of figure out what's a good model for the variation in the current factor, I should basically realize that the variance of my width is proportional to 1 over the length. And that the variance of my length is also proportional to 1 over the width. Again, because these just give you additional averaging. So if I take all this and I just, again, come up with some A parameters that are, again, just coming from the process technology, and I want to figure out what's my current factor mismatch, I can just basically plug all these things in, and what you end up with is something that looks kind of interesting. So these terms right here, those are really coming about because of these edge roughness effects. Those are really like the mismatch in the width and the mismatch in the length. Okay? What's interesting about these ones is, notice they don't just depend on the area of the device, but they actually depend on the area times like the length, or the area times the width. So for both of those, what that basically says is, if you really, really care about devices to match each other, that basically says that you should make sure that you use either a W or an L, or really both, that are kind of large enough to completely get rid of these terms here, right? Because you can see, because they depend basically sort of like, it's almost like it's cubic on the device dimensions. If you just make them either wide enough or long enough, that's a great way of just getting rid of these two effects here, okay? Now, by the way, this does get you into something sort of interesting. Because of the fact that I have these like edge effects over here, if I take one device that, let's say, used to have 2 microns of width and, let's say, 100 nanometers of length, and I split it into 2 devices, like I finger it into 2 devices, where now I have 1 micron of width and 100 nanometers of length. From the standpoint of these edge effects here, are these two going to be the same or different? What do you guys think? How many edges do you have in this one versus how many edges do you have in that one?
Four versus 2.
Right. You got 4 edges here, you got 2 edges there. So, what do you think is going to be? Are they going to be the same or are they going to be different? If I have more edges, what do you think that's going to cause?
More variation.
Yeah, it's going to be worse, right? Because each one of these individually gets averaged less. And so from the edge effect standpoint, I'm actually going to be more sensitive. Okay? So again, what this basically says is, if you really care about good matching, you have to make sure that your unit device is either wide enough or long enough to get rid of these sort of edge effects here. Okay? Because if you make them small and narrow, at some point these will actually come into the picture. Now, this is, of course, in contrast to, if you look at these terms over here, those just depend on area, right? So for those, doesn't matter if you do this or if you do that. Has the exact same matching effect, okay? So again, particularly for things where you really, really care about that matching, you may intentionally not use minimum channel devices. You may intentionally use things that are much, much longer or much, much wider, just to make sure that you've knocked off these edge effects here. Okay? This make sense to people, or? Yeah.
Yeah, one quick question. So, since the W depends on the W mismatch depends on the L and the L on W, so is the first equation valid? Like, you're
This one over here?
Yeah, as a sum of 2 variances, as though they are uncorrelated.
So the assumption here is that the individual phenomenon causing the variation is small, right? So essentially, you're right, there's a little bit of a correlation there, but it's basically just saying, whether or not the photon hit in this spot doesn't really matter if there was a whole bunch of extra material on the right. Right, that's kind of what it's saying. Okay, so actually, you could have questioned whether this model was correct in the first place, because, I have something that looks like W over L, and, so obviously this should really be like a minus 1 over 1 minus x, but I'm just assuming that all of this is kind of small enough that I can do this sort of first-order Taylor expansion. That's kind of what's happening there. It's a good question. Other questions on this, or? Okay. So, as we spent some time actually talking about, again, back in the beginning of class, with all these things, the numbers that I've been giving you have all been sort of assuming that you did the quote-unquote right thing when you tried to match 2 devices. So in particular, the sort of wrong thing that I'm highlighting here is if you actually had 2 devices and allowed current to flow in different directions on those 2 devices, sorry, not going to match. Okay, the mismatch you measure will be very, very different than all these models that I've given you. Because bottom line is, unfortunately, the world is not isotropic. At least, the world of silicon ICs is not isotropic. If you are like a process kind of guy, if you happen to have current flowing in, one of the crystallographic planes versus a different crystallographic plane, the mobility is different. Okay, so bottom line, don't do something like this. Don't try and have 2 transistors that are oriented the other way and try and match them to each other. So if you want them to match, better have current flowing in the same direction. Okay? And in fact, again, as we had talked about sort of a while back, because of this, whenever I build a transistor, I almost always build it as at least 2 fingers, so that I always have current flowing both from left to right and from right to left. So that if I take that thing and then repeat it a whole bunch of times, I'm basically sure that I didn't mess up the current flow directions. Okay, so this thing, as long as I repeat it without turning it 90 degrees, I'm sure that it'll actually have the right matching from a distance or from a direction standpoint. Okay? Now, the other thing that I'd mentioned, this is just, again, some plots from the Pelgrim paper. We said if you put the devices farther away, you get larger mismatch. So obviously, this is kind of one of those, doctor, when I do this, it hurts. Don't do that. Okay? Just don't put them farther away. Keep them close to each other. Again, even if they're really big, turns out you can do that. I'll show you how you do that a little bit later. Okay? So, as I'd mentioned before, all of these parameters actually tend to scale with technology. So the numbers that you get, for example, for that AVT parameter, which is like the proportionality constant, actually turns out to scale with technology. In fact, other of those parameters also tend to scale with technology. But I'm going to focus on the AVT here, because that turns out to be one of the sort of most important ones, and also to scale in the least friendly way with technology. Okay? So this AVT here, it basically is proportional to the oxide thickness, and actually inversely proportional to the doping. Okay? And that kind of makes sense, right? Because that's basically, the oxide thickness tells you how much voltage you need to put on the gate in order to image a certain amount of charge inside of the channel, right? So the thinner you make that oxide, the less voltage you need to basically, essentially, counter some change in the dopant ions, okay? So that's what this sort of plot here is showing you. So the interesting thing to actually look at is sort of what are some of the numbers here. And this is now from the 0.18 micron CMOS process. This is again just showing that it's still following the trend of 1 over the square root of the area. But basically, if you go down to your sort of 0.18 micron process, the AVTH is going to be roughly 8 millivolt micron. Okay? So given that this mismatch is actually proportional to the oxide thickness, so if I told you that AVTH for 0.18 micron is 8 millivolt micron, what do you guys expect that mismatch will be in a 90 nanometer process? What'll that roughly be? If I sort of scale everything perfectly the right way. Just with the oxide thickness just scales with the technology. Yeah, 4 millivolt micron. Okay, because the oxide thickness, at least ideally speaking, is about half of what it used to be. Okay? Now, turns out there's good and bad news here, right? So, the good news is, for this device, if I keep the same area as the device I had in 0.18 micron, I'll get twice lower threshold mismatch, right? So if I had a 1 micron by 1 micron device here, it'll have a factor of 2 less threshold voltage mismatch, at least from a sigma standpoint, than I had over here. So that's the good news. What's the bad news? Yeah, my area scaled by a factor of 4. What's the even worse news? What happened to the nominal value of the threshold voltage? Anybody remember sort of what you typically do with the threshold voltage when you went from 0.18 micron to 90 nanometer? Yeah, it also probably scaled by a factor of 2, right? So my area went down by 4x. My VTH might have gone down by 2x, right? So for the same area, I would have gotten only a factor of 2 reduction in the delta VTH, right? But now, since the area went down by 4x, that means it's actually going to get worse by a factor of 4. and my VTH nominally went down, right? Excuse me, that my area went down by 4x, so it actually only goes up by 2x. So that means that, in other words, roughly speaking, my delta VTH in the 90 nanometer technology, because the area went down by 4 and the AVTH went down by 2, roughly the delta VTH is actually constant with 4x less area, right? So in other words, if I used to have about 100 millivolts of mismatch, I'm still going to have about 100 millivolts of mismatch, right? So by the way, if I was a digital guy, that's really kind of annoying. Because remember, my VDD went down, right? So my VGS minus VT is actually getting worse. Now, even as an analog guy, this is actually kind of an annoyance. Because that basically says that even though I'm scaling the technology forward, I basically have to keep using the same darn device area to get a certain amount of delta VTH, right? That basically means that, scaling doesn't even buy me anything anymore. Just from a sort of power standpoint, if I'm limited from that area. Turns out, actually, life is even a little bit worse than this, because this scaling that I did here was assuming the oxide actually did scale. That's not entirely clear that that's continuing to happen. Okay, so actually, even in like the current designs that I do now, all the way down to about 45 nanometer or so, when I want to just quickly estimate what's the threshold voltage mismatch going to be, I still use this 4 millivolt micron number, because it's not clear the oxides are actually scaling. There's enough other weirdnesses happening that this number here is actually a pretty good number for about 3 or 4 technology generations right now. Okay, it's maybe a little bit lower. I think the lowest I've seen is maybe about 3 millivolt micron, but pretty darn close. Okay, so in fact, I put this even on your project handout. For us, we're going to assume threshold voltage mismatch. AVT is 4 millivolt micron. Okay? Okay, so now that we've sort of just kind of really briefly walked through and seen sort of how all of this, we can model it, what I wanted to just quickly do was see from a design standpoint, should this imply to us about how we should basically choose the V star, or how should we size the transistors to get a certain amount of matching. So let's first start out with current matching. So for this, let's just assume I have a current mirror. Okay? And let's assume it's 1-to-1 for now. And there's basically going to be sort of 2 effects. So one is there's going to be a certain delta VTH. And the second effect is, which I'm just sort of drawing conceptually, is that there's actually a certain delta beta, right, which I've sort of drawn conceptually as a little bit of an extra transistor on the side. Right, that extra transistor basically causes extra current to flow in the output based on what that delta beta actually is. Okay? So, if I wanted to look at the mismatch in current, what would that be given this sort of setup that I've given us here? What would the mismatch in current be? Let's say that this has a nominal beta 2, by the way.
Delta beta by beta.
I heard somebody say something. Just speak up.
Delta beta by beta into I.
Yeah, so first, clearly I have delta beta over beta times ID, right? Because this thing over here, if this has an ID in it, this will have delta beta over beta times ID of extra current, right? Okay, so that's definitely true. What else?
GM times delta VTH.
There we go. Plus GM times delta VT, right? Okay, so now all I want to do is rewrite this thing slightly to give us a hint as to how we should actually size this thing up. Okay, so now I'm going to look at the normalized current mismatch. I'm just going to divide everything by ID. So I'm going to get delta beta over beta plus GM over ID times delta VD. Okay? So, what is GM over ID? What's our sort of favorite parameter that we like to use all the time to replace GM over ID with? V star. Now, there's actually a factor of 2 there. That turns out to be 2 over V star. Because remember, GM is 2 ID over V star. Okay, so delta ID over ID turns out to be delta beta over beta plus 2 over V star times delta VT. Okay? In other words, to use our sort of AVT and A beta parameters, that says that the variance of delta I over I is just going to be A beta squared divided by the device area plus 4 AVTH squared divided by V star squared, again, times the device area. Okay? So now, as should hopefully be glaringly obvious, and we kind of touched on it several times already, if I have a current mirror, how should I choose V star in order to try and minimize the mismatch that I get? What V star do I want?
Large.
Yeah, I tend to want large V star, right? Because the larger I make the V star, in essence, if I can make this whole term here go to 0, then I can just be dominated by that A beta term. Now, what's the only minor fly in the ointment with making V star large?
Voltage swing.
There is the voltage swing. What else? Yeah, you started saying it.
You eat up your headroom.
Okay, you eat up your headroom. Same thing. There's one other, remember, what does making V star large translate into?
Power. Your efficiency is like.
Okay, your power efficiency is bad. I agree with that too. Let's say that this is a current source, so this doesn't even set like my GM, so that's not directly affecting my power efficiency.
Small w.
Ah, there we go. Right? If I make V star big, that basically means I'm making the W small. Right? Because there's a certain current density associated with that V star. So in fact, if you take a look at it, oftentimes, there turns out to be a certain optimum V star that gives you the minimum current mismatch. Okay? Because if you make the V star too large, your device becomes really small, and so on the net, things actually get worse. Okay? But nominally speaking, that does say you probably don't want to make the V star too small, because indeed, you'll amplify up that threshold voltage mismatch by a large factor. Okay? Just again, be careful that W and L actually depend on that V star there. Okay? So as an example, if you really, really want to make devices with really good matching, what you should probably do is choose a large V star, but then if you want to get even better matching, you keep the V star fixed, but just multiply both W and L up by a factor, right? And that's basically how you could really knock down this overall term. Okay, if you leave the L fixed, then actually playing with V star is the same as playing around with W, and so you have to be careful with which one becomes the dominant factor. Okay? Okay, so just like, of course, we might care about current mismatch, what you probably care about even more, particularly from the standpoint of your project, is voltage mismatch. So let's go ahead and draw, let's just say I had some differential pair, where again, there's some delta VTH, and some delta beta. Okay? So, if I wanted to know the input referred voltage offset, what would that be for this diff pair here? Well, let's start with the simple term. What's the simple term? So again, I'm just looking at, this is, let's say, VI plus, and that's VI minus. So what's the offset that I would measure from this thing?
WTH by 2.
Oh, it's actually just delta VTH. There's no divide by 2 because, right, it's just a voltage source, directly in series. Okay, so there's a delta VTH. That's certainly there. What else am I going to get? What other factor is going to translate into input referred offset?
Delta beta by beta into ID by GM.
There we go, right? So if I have this extra delta beta over here, that means that even for the very same input voltage, I have some delta ID of current flowing out there, right? So what I need to do is translate that delta of ID of current back into a voltage at the input, which, as Shiva just said, is going to be delta beta over beta times ID divided by GM. Because to get from current at the output to voltage back at the input, you just divide by GM. Okay? So now, just like before, I can sort of tweak this around a little bit, because again, GM over ID is just directly basically V star over 2, right? So that just becomes delta beta over beta times V star divided by 2.
Is there a factor of 2 over there?
There is indeed a factor of 2 there. Because remember, GM is 2 ID over V star.
I mean, in the first line,
So this ID here, if this is IB, that ID there is IB over 2. Oops, sorry. There. So when I said ID, I was really referring to the nominal current flowing through here. Okay, but there's no factor of 2 on this point. Because again, for the same input voltage, this is the delta ID that I get out. Does that make sense? Or? Okay, if not, you can come bug me afterwards. But here there was no factor of 2. This is actually correct. Okay? So once I've done this, then again I can go back and say what's the sigma of the voltage offset? And that's just going to be AVTH squared divided by WL plus A beta squared times V star squared divided by 4 WL. Okay, well, so again, if I care about small input referred voltage mismatch, what do I want to do? Do I want to make V star big or V star small?
Small.
Yeah, I want to make it small, right? Because basically the smaller I make it, the less the effect that beta term is going to have. It's kind of like saying that my gain is really big, right? Because if I have some small amount of current mismatch, if my GM is really big, from an input referred voltage standpoint, that doesn't have as big an effect, right? So for current matching, generally big V star. For voltage matching, generally small V star. Okay, with both of them just with the caveat of watch out that the area depends on V star. Okay? Does this make sense to everybody? Or? By the way, this should be sort of totally expected, because if you remember all of our discussions about noise, we basically said the same thing, right? We said for noise, we want current sources to have big V star and differential pairs to have small V star, right? So exact same thing happens here for the exact same reasons, because you can almost think of mismatch as like DC noise, okay? So I think I'm maybe going to skip over this really briefly. We'll come back to it next time, because there's just one sort of thing that I wanted to mention before we break for today, because it's really related to your project. And that's basically, how do you actually go about simulating mismatch? How are we going to go about sort of dealing with this from the standpoint of checking that everything is actually okay? Well, so it turns out there's basically something called Monte Carlo methods, which what they literally do is they have HSpice. They tell it, okay, all of these parameters vary with the following distribution. And to simulate that, HSpice pretty much literally just throws the dice, picks something from that distribution, simulates the circuit with that particular mismatch, and then tells you what the result is. And then it repeats that a whole bunch of times. Okay? So as an example, a very common thing to do may be something like, take your differential pair, build some deck that measures what's the input referred voltage offset, and then run this Monte Carlo simulation through HSpice. Okay? So let's just plot a couple of things here. So as we'd said before, since all of these sort of variations are supposed to be Gaussian, you'd basically expect that if I looked at the probability density function, or the PDF of the offset voltage, you'd expect that it looks something like a Gaussian, right? Which, again, excuse my poor drawing, but looks something like a Gaussian. So now, when you go and you do this sort of Monte Carlo simulation in HSpice, Gaussians, unfortunately, go out infinitely long on the tails, right? So I don't know about you guys, but I don't really want to wait for HSpice to run 10 to the 15 or 10 to the 20 simulations, because even with really great computers, that takes a really, really long time, right? So usually when you do something like this, what you actually will do is you'll tell it, okay, do like 100 Monte Carlo runs. What that means is it'll pick like 100 discrete points from that distribution. So when you do that, what you'll usually get back will look something approximately like this. So if that's the offset, and this is like the probability that you solve that particular offset on your 100 Monte Carlo runs, you'll see something that'll maybe look like, and I'll just change color to make it more clear. It'll maybe look like, okay, you'll have a bunch of them sort of centered around there. You'll have maybe some more over there. Maybe you happen to not get that many here. And then it kind of roughly does the right thing. And then on the other side, it may look, I don't know, something like that. Okay? So, this thing looks sort of like a Gaussian distribution, but clearly I only had 100 samples, right? So I can't really know what the real distribution is. So kind of the key point here is when you do these Monte Carlo simulations in HSpice, be very careful with how you interpret the data. Okay? So definitely don't assume that whatever the distribution that comes back is the real distribution, because it's highly unlikely you did enough simulations to really figure that out. So really the only thing that you can kind of trust out of these sims is, well, obviously the mean. That's pretty reasonable. You have 100 samples. You can kind of calculate the mean pretty well. And then if you really, really do enough sims, you can maybe trust the sigma. Okay, you can maybe trust the sort of the variance that you've gotten there. But even that is actually a little bit questionable because you really need a pretty large number of samples to estimate that pretty reasonably well with any kind of confidence. Okay? So bottom line, when you do these sort of Monte Carlo simulations, just be very, very careful with how you look at that data, because it's not the real distribution you're probably going to get. It just is telling you some aggregate characteristics. That's the only thing that you should look at and kind of trust with any amount of confidence. Now, by the way, if you couldn't tell already, I'm actually not the biggest fan of Monte Carlo simulations. Okay? Because, as I'll explain in one second, I claim that I've almost, I can count maybe on one hand the number of times I actually ran a Monte Carlo simulation and learned something that I shouldn't have known already. Okay? Yeah?
Looking at the different corner models?
Yes and no, because remember, corner models only shifts all of the transistors together. Right? Because you can't tell it, okay, put the left transistor in FF and the right transistor in SS.
Yeah.
Right? It only shifts them all together. So this Monte Carlo, that's literally taking the VT inside of each individual transistor and tweaking them differently. Okay? So, as I'm going to explain in one second, I actually believe there's a much better way for you to sort of to handle these kinds of simulations, and that's what I'm really going to force you to do in the project. And the way I'm going to force you to do that is I'm not going to give you any way to actually run Monte Carlo. So I haven't done anything inside of the models or anything like that that would actually let you do it. I suppose you could write a Perl script and do it yourself, but I'll still bash you on the report afterwards. So what I actually claim is the right way for you to simulate mismatch, and what I do 99% of the time, is basically, well, this is going to be a little bit ironic, but essentially the way I claim you should simulate mismatch is always calculate it first. Okay, in other words, don't simulate it. Calculate it. Because you have all of the parameters you need to actually figure out what the mismatch should indeed be. Okay? So in other words, if you do some Monte Carlo simulation, that should really be only to verify your calculation. But I claim that even once you've done that Monte Carlo and you have the sigma and it matches with what you calculated, I claim that what you should actually do is just take that mismatch that you calculated and add it into your circuit deterministically. So what I mean by that is, basically take your diff pair, let's say. If you calculated that the sigma of the delta VT was, let's say, I don't know, 10 millivolts, you know how much yield you want to get. As an example, if you want 3 sigma of yield, then go in and add in your circuit directly 30 millivolts of offset onto that differential pair. Okay? And then just simulate the thing. Because trust me, this is way, way faster than running 10,000 Monte Carlo runs and trying to see if each individual one of those things actually worked. Right? You basically this is almost like the statistical version of doing a worst case analysis. Okay? So from the yeah.
Don't you need the AVT values?
So I gave it to you. 4 millivolt micron. Right? So you're right, even in some general process you need the AVT, but I claim if you're going to be designing stuff, you need that AVT, right? Because otherwise how are you going to know how to size the thing, right? So essentially from the standpoint of the project, what you should really be doing is go in, calculate what the 3 sigma offset for each matched pair is supposed to be. Once you know that, just plug it into your circuit and simulate with that offset inside of it, okay? So the only other thing that I'll just sort of really briefly mention is, remember, mismatch is always between a pair of transistors. In other words, if I draw a differential pair, that AVT is the AVT between the pair, okay? So just be careful with that because it's very tempting to like take a single transistor and add some AVT onto it. That's not how it works. It's always between a pair of devices that you get that mismatch. Does this make sense to everybody, or? Okay, so we'll just finish up with some of the layout techniques on Tuesday and then really move on to talk about how we're going to deal with this mismatch. So see you guys then.